Hello everyone, my name is Baifan Zhou. I'm a PhD candidate at the Bosch Corporate Research and the Karlsruhe Institute of Technology. The paper I will be presenting today is titled with Predicting Quality of Automated Welding with Machine Learning and Semantics, a Bosch case study. The paper is the joint work of 6 authors affiliated with 3 universities, Bosch Corporate Research and Bosch Center for Artificial Intelligence. In the center of our use case is an automated welding process named as resistant spot welding. It connects metal sheets using high current to materials and form spots. It is worldwide applied at the Bosch plants and Bosch's renowned customers. The diverse data are collected from many sensors, plants, customers, and therefore there are many data sources. And the data amount is enormous. For example, a car can have up to 6,000 welding spots. Quality for all welding spots is important. The quality failure of one single spot can cause the entire production line to stop. This means loss of time, several cuts, and cost of maintenance. On the right-hand side, the welding process is illustrated, in which a welding machine moves along the worksheets, generating welding spots consecutively. The spot diameter is an important quality indicator for of the spot, but it is extremely costly to measure in production. The Bosch solution is to instead use Q value. It is an empirical quality indicator calculated based on sensor measurements. Its optimal value is 1. When its value is less than 1, which means the quality of the spot is deficient. When its value is greater than 1, it means too much energy was spent on that spot. The goal of our paper is to predict the quality of welding even before it happens. We propose using machine learning with feature engineering for welding quality prediction. In our proposal, there are 2 versions of machine learning pipelines. The simpler version is named as the base pipeline, in which the padded time series go through feature engineering and the time series features engineered are then concatenated with raw single features, and then they are reshaped to include the data of previous welding operations. The reshaped data can be modeled with 2 ML algorithms. One is linear regression after flattening and feature selection. Another one is a rather complex LSTM neural network. The feature engineering algorithms for time series are get time series statistics, or get TSStats for short. It extracts 8 statistic features from the time series, partially illustrated on the right-hand side. The complex version of our proposal is named as the full pipeline, which is built upon the base pipeline, adding 2 extra feature engineering procedures. One is the feature engineering on raw single features, which generates a series of engineered single features. The second one is advanced feature engineering algorithm, which takes engineered single features and time series features engineered as input and performs decompose algorithm with respect to a welding program. Due to time limit, I will not go into detail of this decomposed algorithm. Now we have 2 versions of the pipelines. So how do they perform? How well do they perform? The upper part of the slide shows the illustration of the prediction results on 2 welding machines with the line plot and scatter plots. We can see that the prediction results on the test set, drawn by the green lines, follow very closely to the ground truth target, drawn by the black lines. This gives us an impression of good performance. To get a detailed understanding, we use the metric mean absolute percentage error, or MAP. It is illustrated on the bottom right table. In this table, when we compare the ML models of the full pipeline to their counterparts of the base pipeline, we can see that all 4 pipeline models are better than the baseline models. And since the full pipelines have a higher degree of feature engineering, this means feature engineering can improve the ML performance. We also see that the linear regression models are also providing good performance. And interesting to see is the linear regression model of the full baseline even outperforms LSTM for the machine 1. We postulate the reason is because machine 1 has less complex data, and for this kind of complexity, if adequate feature engineering has been done, linear regression can also provide good results. Now we have good prediction accuracy, but it's not only the only important metric for adoption of ML pipelines in industry. In our Bosch industry use case, we introduced 6 metrics to evaluate the adoptability of ML pipelines. These metrics are the required time for domain understanding and feature understanding, how efficient or generalizable data preparation is, the required effort for hyperparameter tuning, the average training time, and how easy the models are to understand or to explain, especially for non-ML experts. Subjective evaluation to these metrics are given by our project members. And we can see the average score on these 6 metrics result in a score of 2.7. This is fairly good, but in our Bosch setting, we have increasingly strict requirements on adoptability, and we need to improve the adoptability. To improve this, we propose to rely on semantic technologies. Our semantic solution follows in 3 steps. In the first step, it is data preparation. And in this step, the raw variable names need to be annotated with the domain ontology names, which are domain ontology terms in domain ontologies created by the process experts, based on which annotations of ML feature groups, feature processing algorithms, and feature process groups can be automatically reasoned from ML ontologies. As long as the raw feature names are annotated with domain ontology feature names, our smart semantic algorithm can infer feature group annotation from the ontological mappings, and it can automate ML analysis pipeline by activating feature processing algorithms step by step, and at the end, the ML modeling algorithms, constructing parameterized ML pipelines automatically. The semantically enhanced ML with feature engineering is also evaluated by our project members. They gave, at the end, the average score of SEM-FE is 4.0, which is significantly better than the score of 2.7. This is a result of the improvements on 4 out of 6 metrics of adoptability. In conclusion, machine learning is a powerful approach that can do good prediction for automated welding, and feature engineering can improve model performance. For evaluating adoptability, we have introduced 6 metrics. And semantic enhancement can improve adoptability, and the results are evaluated. In the future research, we will investigate more ML methods, such as feature learning and more complex welding machines. We also plan to integrate the ML pipelines into a new online welding control system and automation platform at Bosch. Thank you for your attention.